Now that we've seen how to define an exponential function, like say 2 to the x, where x is any rational number, we want to review the properties that these exponential functions have before trying to generalize to the reals. So the first important property was this f of x plus y equals f of x times f of y. And recall that this was the key ingredient in reasoning about how we should define, say, 2 to the power 0 or 2 to the power minus 1. We chose those definitions so it satisfies this property, and therefore when we generalize to the reals, we want to be sure that we keep this property as well. Another important property is that these exponential functions should only output positive values, because we're in the back of our heads thinking of these as supposed to be taking a positive number and raising it to some power x. So you might reasonably ask that the function you get by generalizing that should also only output positive values, since a positive number to a positive power should be positive. And the third thing, which I didn't discuss but will be important, is we're going to assume that our exponential functions are always either strictly increasing, strictly decreasing, or constant. So what do I mean by that? Strictly increasing means if you have two numbers, a and b, and a is larger, then the function will always output a larger number when you feed in a than when you feed in b. So this is just a function whose graph is always going up as you move to the right. Likewise, strictly decreasing means if a is greater than b, f of a is less than f of b. And constant is fairly self-explanatory. Constant means that the function always outputs the same value. So to see why it could be any of those, let's think about, for instance, the function 2 to the power x, which has this graph. So as you increase x, you're multiplying 2 by itself more times, so that always gets larger. So this function is strictly increasing. But if we took a fraction less than 1, say 1/2, and raise that to the power x, now as x increases, you're multiplying 1/2 by itself more and more times, which makes it smaller and smaller. So this function is strictly decreasing. As you increase x, the output of the function gets smaller. And now the only example of a constant exponential function is the function 1 raised to the power x. So when you take 1 and raise that to any power, it's always going to return 1, because 1 is this multiplicative identity. So this is our wish list. We know that the exponential function on the rationals, which we just saw how to construct, has these properties. So now we're going to ask that when we extend it to a function on the reals, it still has these properties. Okay, so with that motivation, let me present the definition. So this is going to be the definition of exponential function, and it's the one given in the textbook. So we say an exponential function f, so this is the definition, and f is the function which is said to be exponential. An exponential function f is a strictly increasing, strictly decreasing, or constant function, so it could be any of those three that we saw on the previous slide. We assume it has a domain R, the reals. We assume that second bullet point, that it only outputs positive values. And most importantly, we assume that that function has the property f of x plus y equals f of x, f of y, for all x and y in its domain, which is the reals. So it seems like we've just made a wish list, but this is actually a precise definition of what we mean by an exponential function whose domain includes the irrationals. And this is a very common strategy in mathematics. If you can't construct something, if you don't have a constructive proof, like a way to define 2 to the power pi, you basically list all of the properties that you expect that function to have. And then if you can prove that there exists some function with those properties and that it's unique, you're done. You don't need to give an algorithmic way to compute 2 to the pi, because you've proven that it exists uniquely, so you've defined it. Okay, so this is the approach the textbook takes, which is to say, this is what we mean by exponential function, and then later in the book, I think in chapter 5, we prove that such a function exists and is unique. So this is one way to answer the question of what 2 to the pi is, but it's kind of roundabout. It's non-constructive, which means we prove that there's a unique number, 2 to the pi, defined by these properties, but it doesn't really explicitly tell you what it is. So I want to show you one more thing, which is not in the book, but this is kind of one way that I like to think about it. What if you just wanted to define, say, 2 to the power pi, or 2 to some irrational power directly? We can actually do that with the tools that we've seen so far. So what we'll do is say, we're going to define 2 to the power pi, and what we're going to do is take the set of all 2 to the power r, where r is rational, and it's less than pi. So whenever 2 to the power r is, when r is rational, we can use our previous definition. So we use the definition of 2 to the power p over q, which we saw in the first video. So that lets us precisely define all of the numbers in this set, and then this set consists of those 2 to the r for all r less than pi. And now to define 2 to the power pi, we take the supremum of that set. So we've seen what supremum is. This is basically taking the number line, and there's all these numbers which come from rationals that are 2 to the power r for r and q and r less than pi. And there's this whole, because pi is not rational. So there's this whole here, and this is the supremum of that set. So why is this a good definition? Well, we're guaranteed that that supremum will exist because we saw in the reading of chapter 1 that the reals are complete, which means any set with an upper bound has a least upper bound, which is called a supremum. So since this set is bounded above, we're guaranteed the supremum exists, and we are also guaranteed that it's unique. There's only one number with this property, which was proven in problem 1.6 of AOPS. Okay, so this is another way to define this 2 to the power irrational number. And we'll see that this is actually equivalent to the first one, but just as a teaser, let me give you one more way of defining 2 to an irrational power. So this will seem like magic at this point. But one can actually show, and we'll do this later in the book, that using either of those two definitions above of exponential functions, you can prove that any function with those properties, either a function which satisfies that wish list in the definition, or a function who's defined on the irrationals by that supremum argument, any function with that form can be written in a very particular way as an infinite sum of its argument x and some numbers a and b. This is very strange. It's surprising, I think, because the other definitions made no reference to infinite sums. We just had one where there was this list of properties like f of x plus y is f of x, f of y. The second one was this supremum argument. So I find it really quite magical and impressive that either of those definitions constrains the function so tightly that it has to look like some infinite sum like this. Okay, so that's another way to define 2 to the power pi, which will make more sense later. But just to review, so we saw a definition of exponential functions in terms of a certain wish list of properties, and for now all we need to know is 1, what those properties mean and how to prove things about exponential functions using those properties, and 2, that these are enough to uniquely determine the function. So these assumptions are enough to pin down precisely what a number like 2 to the power pi means. Okay, that's all for today.